Okay, so this is Edexcel C1, Chapter 7 on differentiation, and we're starting at section 7.6 in this video. So, first of all, apologies if it's even less coherent than usual. I'm, as you may know, not feeling too excellent today. So, section 7.6. Now, by this point, we've done talking about differentiation. We've practiced differentiation quite a bit. There's only a few extra little bits to finish off, and so we'll do the whole chapter, all the last 3 parts of this chapter, all hopefully quite quickly here. So the first thing is, if we take a function, let's say we take x to the power of 5, and we call that our function y, if we differentiate that, we get what we call dy by dx, and then we get 5x to the power of 4. What if we decide we want to differentiate again? It's something we often do, isn't it? If you once we learn to do 2 plus 2, then we do 2 plus 2 plus 2, and then we keep going, and then we end up with, well, if we end up with 2 plus 2 plus 2 plus 2, when it gets a bit difficult, we end up calling that 2 times 4. So whenever we've got a new toy in maths, we like to see what happens if we use it once, use it again, and see where we get to. So if we were to differentiate this again, we'd end up with 20 x to the power of 3. Bring the 4 down to the front, times it by the 5, reduce the power by 1 on the 4, and it turns into a 3. So we need a notation for that, and this is the notation we choose. d2y by dx squared, okay? And it's that simple. If you're asked for this thing, it's called a second derivative. It means differentiate the derivative. Excuse me. In the f of x notation, instead of calling it f dash, we just call it x dash dash, or x, f dash dash or f double dash. So these two things here, these are both different notations for what we call the second derivative. The second derivative is where you differentiate the derivative. Now, the second derivatives have got various uses, but none of them we really need to know about as far as this C1 textbook and the exam is concerned. I'll give you a quick idea of some ways of thinking about it, but essentially the second derivative is just what you get when you differentiate a derivative. If you want to leave it at that and just think of it as the sort of thing we do in maths, once we've learnt to do one new trick, we see what happens when we do it twice, and we need a notation for that, then that's absolutely fine. Just a couple of extra notes on it then. First of all, this notation d2y by dx squared, it's a bit weird that the 2's go sort of here and here, and the reason for that is that this d by dx notation is, we see it as dy by dx, and it looks like a fraction, but what we're really doing, it's not actually a fraction. What we're really doing is taking the function y, and we're doing this d by dx thing to it. We're kind of differentiating, so you can see it as sort of taking this d by dx and doing it to this function y. So that's where this sort of 2 notation comes from. It's the d by dx that gets the 2's on it to show us we've done it the second time onto the function y. So if you're confused by that notation, that's sort of the origins of it. The second thing is, well, how do we think about a second derivative? What's the relevance of it? We'll get more into this in C2 and see how we can use it as a mathematical tool, but for the moment, a way of thinking about it is, if you think about dy by dx, that's a gradient, isn't it? And another thing that we've been calling it is a rate of change. So it's how does y change if we change x a little bit. So if you have your displacement, which if you know any physics, or if you do mechanics, you know displacement, we give the letter s. And if we look at rate of change of displacement over time, so that is how does your position change if we change time a bit. Well, that's what we call speed, isn't it? How does your position change with time? That's what we call the speed. So how many miles do you go in an hour? Miles per hour. How your position changes with time. Okay, so that's speed. What if we look at the rate of change of speed? So speed itself is a rate of change. It's change of displacement with time. So what's the rate of change of speed called? Well, that's called acceleration, isn't it? How is your speed changing over time? So it's the rate of change of a rate of change. So if you take something which is already a rate of change, like speed, how does that change? That's a second derivative. Another thing to think about is, the other example I often use is inflation. So in economics, the inflation is a rate of change. It's a rate of change of the value of things over time. How is inflation changing? What's the rate of change of inflation? Well, that's the rate of change of the rate of change of the value of things. Okay, if that sort of makes sense. So if you have a rate of change and you want to see how that is changing, that's what we need the second derivative for. That's the sort of that's what it represents. Okay, the second thing then in this video is section 7.7. And we have things like this. Instead of x's and y's, now again, there are two ways of thinking about this. Firstly, just what we need to know for this, sorry, that t's gone a bit funny. So I'm doing the first question from the exercise here. What we need to know for the exercises, for the textbook, for the exam, is just this. Here we don't have x's and y's anymore. As you know from other areas of maths, we don't always use the letters x and y. Sometimes we use different letters. And in this example, we've decided to use the Greek letter theta and the letter t. So if I wanted to look at this and think about differentiation, I wouldn't do dy by dx, I'd do d theta by dt. Okay, and this is just a little exercise to point out to you that you don't always have to use x's and y's. So this exercise is as simple as that, exercise 7g. It's not always got to be an x and a y. The thing that's on the top, you treat it like the y. The thing that's on the bottom, you treat it like the x. Okay, this is what we call the derivative of theta with respect to t. That's pretty much it. Another way of thinking about this, though, if you want a bit more information as to why the way to think about these things and why we might want to consider this, well, the rate of change of y with respect to x means if I change x a little bit, how does y change? We already saw a couple of slides ago, if I change s, my displacement, with respect to time, then that's what we call speed. If I change my velocity with respect to time, then that's what we call acceleration. So the rate of change of this thing, the top thing, with respect to the bottom thing, means if I change the bottom thing a bit, how does the top thing change? In different situations, that can mean different things. So it's reasonable to think about that when we've got time on the bottom. As time goes on, how does the other thing change? In the example, though, they give us dv by dr. So they're talking about, in the example, the volume of a sphere. So how does volume change with respect to the radius? So what that means is, if you change the radius, how does the volume change? And what we find is that dv by dr for a sphere is 4 pi r squared. I'm just looking here at example 12. So dv by dr is 4 pi r squared. So what that means is, how does the volume change with respect to the radius? Means if I change the radius a bit, what happens to the volume? And the answer is, it depends what your radius is. If you tell me how big your radius is, I can tell you that if you make your radius a bit bigger or a bit smaller, I can tell you sort of how the volume is changing at that sort of size of the radius. So if we say we started with the radius of, let's say the radius was 3 units, so that would be 4 times pi times 9, so 9 times 4 is 36 pi. 36 pi, so pi is about 3, so we're looking at, I don't know, roughly 110-ish, something like that. So sorry about that, something funny happened, I don't know if there's a hiatus in the video. So when the radius is about 3 units, the rate of change of the volume is about 110 units. So if you're increasing or decreasing, you can think of that as the gradient. If you plotted a radius here and a volume here, if you increase the radius, the volume would change in this sort of way. So if the radius axis is here and the volume axis is here, the way the radius and the volume are linked, we already know is 4 over 3 pi r cubed, so it's going to look like a cubic. And the gradient of that graph is, when r is 3, the volume is about 110. So if this is 3, this is about 110. Sorry, the gradient of that graph. So this gradient here is about 110. When r is 4, then this gradient here will be 4 times pi times 16, which would be a different number again, so the gradient would be bigger, and so on. I don't want you to worry about all that sort of detail too much. For some people, it helps to try and sort of think about what these things represent. For a lot of people, though, to start with, just take this exercise as there's a different letter on the top, there's a different letter on the bottom. Pretend the top letter's a Y, pretend the bottom letter's an X, and keep going the way we already have with all the other exercises. Don't get bogged down in the detail. The intuition of how this stuff works will come with time, but I've tried to give you as much explanation as I can. It's a little bit difficult until we get further into it to be able to give you more information, so it's a little bit chicken and egg, this particular topic. For some people it's a bit uncomfortable to know to sort of plough ahead without knowing what we're doing, but it's difficult to understand what we're doing until we've practiced some of the skills. So if it is uncomfortable, don't worry about it at the moment. Just crack on through the exercise, assuming that the top numbers are Y, the top letters are Y, the bottom letters an X, and pretending that that's what it is. Okay, so final bit, section 7.8. Now, unusually, what I'm going to recommend, if you look on pages 128 and 129, there are there's two bold bullet points which start with the phrases, the equation of the tangent to a curve at a point is, and the equation of a normal to a curve at a point A is. Ignore those bullet points entirely, is my advice to you. What they've done is they've taken the technique I'm about to show you and they've tried to put it in a nice, neat, handy formula. The problem is, I think that the nice, neat, handy formula is a lot harder to use than just knowing what the technique is. And I think most people find that. I don't know anybody that's actually kind of gone through the exam using these formulas and liking them. Obviously, if you try my technique and you dislike it, then go back and look at those formulas, see if that helps you out anymore. But my strong advice is don't use those formulas. Just think about what's going on. So first of all, in this section, what we're trying to do is we'll have a curve and we'll have a point on that curve, and we'll want to find either the equation of the tangent, as I've drawn here, or the equation of the normal. Now, if you're not familiar with that word, the normal, it means the line which is perpendicular to the tangent. Okay, so you could say that it's perpendicular to the curve at that particular point, but again, we have this problem of what do you mean by being perpendicular to a point? That doesn't make sense, so it has to be, it's the line that's perpendicular to the tangent. And so, what we're going to do then is, let's take the example in example 13. We've got a curve which has this equation, and we're asked to find the equation of the tangent at the point 3, 5. So using our differentiation knowledge, we see that we've got a curve and we want to find the tangent. Well, if we want to find the equation of the tangent, we want the gradient and the y-axis intercept, y equals mx plus c. Or if you prefer the y minus y1 equals mx minus x1 formula, we need the gradient and a point, x1 and y1, a point that line goes through. So one of the things we need to find then is the gradient. Whichever of these two formulas we're using, we want to find the gradient. And if we're dealing with a curve and we want to find the gradient, what have we got to do? Well, we must have to differentiate. So dy by dx, and again the example has done the work for us, so 3x squared minus 6x plus 2, there is our gradient. Now, that's the gradient of any point on the curve. We want the gradient at this point here, and we can do that as well. So at 3, 5, and again the example does the work for us. If we substitute the x-coordinate of 3 into this expression here, we're going to get 11 out. So at 3, 5, the gradient is 11. Okay, so there's our 11. So what we've got, and this is the way I prefer to do it. In fact, you know what? Let me say it like this: the gradient is 11, and the line goes through the point 3, 5. Let's forget everything that we've just done. We're looking for the equation of a line which has a gradient of 11 and goes through the point 3, 5. Now that is a chapter 5 question. We don't need to do anything else from chapter 7. If you prefer the y equals mx plus c method, use that one. If you prefer the y minus y1 equals mx minus x1 method, use that one. But at this point, I'm not going to carry on with this example because it's not a chapter 7 question anymore. It's a chapter 5 question. It's all about using the techniques that you have for finding the equation of a line if you know the gradient and you know a point that it goes through. So that's that. If this question had asked us to find the equation of the normal to the curve, well, we know that the gradient of the tangent is 11, We know the normal is perpendicular to the tangent, so the equation of the normal is minus 1/11, and we'd work from there. So use your differentiation knowledge to find the to find the gradient of the tangent to the curve at the point we're talking about. Once you know the gradient of the tangent, if you need it, you can find the gradient of the normal, and you know then that you're trying to find the equation of a line when you know the gradient and you know a point that that line goes through, and we can already do that with Chapter 5 techniques. The rest of the chapter, then, the mixed exercise, all the exam questions that come up on this chapter, are just asking you to do exactly one of the methods that we've seen, or be a bit more inventive. Think about those methods and maybe come up with something a bit clever using those methods. So there isn't anything else. All the mixed exercises can be done with the techniques that we've seen. That's the end of Chapter 7.